Yes, welcome everyone. Yesterday we began looking at zero knowledge proofs and went through some examples. Today we want to continue the same zero knowledge proofs. I want to begin by looking at I'll begin with this example 5. Then I'll come back to example 4 later. I'll come to example 4, maybe towards the end of today's lesson. But I want to begin with this example 5. And example 5, I just want to look at how two users would use zero knowledge proof to transact. So I have two persons here. I have person A and person B. Person A is the one that wishes to perform a transaction using Zcash. So that this transaction is zero knowledge proof, such that the viewers on the blockchain may not see the details of the transaction. So you know that there are people on the blockchain who are also viewers there. They're not supposed to see the details of the transaction that a person A is making. So the transaction will be in terms of amount transferred, the address to which the transfer is made, and so on. So he wants to conceal this information so that any other person may not be able to see what the transaction is. Then there's this person B. You remember we said we have the prover and the verifier. So the prover is the person who has the knowledge, the information, and he doesn't want this information to be revealed to the other person. So the other person I'm referring to is the verifier. So we have the prover and the verifier. So the prover has some information he wants to conceal so that the verifier may not know what that information is. But the verifier is interested in having the prover prove that indeed he's aware of that information. Of course, without concealing it, without revealing what the information is. Without revealing the information, he's supposed to do some steps just to prove that he has that information. So you have these two persons here, the prover. The prover wants to do some transaction. So it's this prover that knows the amount in his wallet. It is this prover that knows the address and so on. And he doesn't want this information to be known by other viewers on blockchain. Now, so person B, who is the verifier, is the one who wants to receive this Zcash from person A. So this verifier does not know some information like the amount in the wallet of A. This information, only A has it. Only A has this information. So now person A proceeds, does encryption, encrypts the transaction. So that you see, encrypting it is, he wants to ensure that people on the blockchain, if they were to see the message, they'll not know what it means. So he encrypts this message, the transaction that he wants to make, and then puts it on blockchain. And then the other thing that person A will do, you remember this is the prover, is the one who wants to send Zcash to person B. So person A, the other thing he'll do now, using zero knowledge proof, he will send his proof, the zero knowledge proof, together with the encrypted transaction to the verifier, not to the blockchain. He sends this, the ZKP, that is a zero knowledge proof, together with the encrypted transaction to the blockchain. And so why is this sending this? This one is sending the proof just to confirm that the transaction is legitimate. That is why it's including the proof for the transaction. Now, so we have the nodes on the blockchain. The blockchain has nodes, and the nodes on the blockchain has various functions. Part of the functions is to confirm the legitimacy of the transaction. That is part of the functions of the nodes. So the nodes perform various functions on blockchain. So now the nodes on the blockchain will then verify that this zero knowledge proof that was provided by person A is legitimate. And therefore, person A's encrypted transaction is also legitimate. So it confirms that this proof is okay. The proof that has been provided by A is okay. And if that is okay, then it means that the transaction, that encrypted transaction by person A is therefore legitimate. Now, since the nodes have confirmed that that transaction is legitimate, person B can now agree to proceed and do transaction with the person A. So person B now agrees to proceed with the transaction. And because person B has agreed, what then happens is that now the Zcash will then be transferred from person A's account to person B's account. Now, all these transactions has happened, but what has been happening is there has been information, person A has concealed the information. In fact, at the end of at the end of the conversation, person B does not even know the amount that person A has in his wallet. But the only thing that will move from person A's wallet is the amount they agreed to move from his wallet. So what they agreed to move is what will move, what is in that transaction. But the rest, nobody can know what it is. So it's a zero knowledge proof that has assisted person A to achieve this. So that although he's doing this, his information is not made public to the people he's transacting with, and it's also not made public to the people, other viewers on the blockchain. So you can see how important this zero knowledge proof then is. Now, so what are the classifications, or what are the types of zero knowledge proofs? What are the types, or what are the classification? And that is what I want to look at. And I've said that zero knowledge proofs are classified depending on the quantity of messages that are transmitted. So that's how we classify them. They're classified depending on the quantity of messages. So there are two types, therefore. There are two types. The first type is the interactive, and the other one is non-interactive. Their definition, and of course, from the word interactive, the word interactive as it means, interactive zero knowledge proofs require numerous rounds of backs and forth communications. There's back and forth communication. What that means is this. For instance, yesterday I gave an example where Alex was working with Wanjiru, and then Wanjiru claims she can give, by looking at a tree, she can instantly tell Alex how many, she can instantly tell the number of leaves on a tree. Now, so then they proceed. They proceed. Alex wants Wanjiru to prove that she has that ability. That by looking at a tree, she can know how many leaves are on that tree. So they proceed, they agree on how to proceed. So Wanjiru looks aside, Alex plucks 10 leaves, and then asks Wanjiru, how many leaves have I removed from this, from the tree? Then Wanjiru looks at the tree again for a moment and tells Alex that you've removed 10 leaves. So Alex is not convinced. He proceeds and takes other leaves, like Wanjiru is facing aside again. Alex plucks, let me say, 5 other leaves. Then asks Wanjiru, how many have I plucked? So Wanjiru looks at the tree again and then says, this time you've plucked 5. So this process can continue for a while. This is what I mean by back and forth communication. So Alex will ask as many questions as possible, even 10 times or 20 times or even 30, until he's convinced that indeed Wanjiru has this ability. So this is what we call the interactive zero knowledge proof, interactive. There's a lot of communication, there's a lot of questioning and a lot of response. Question, response, question, response. So that proceeds for a long time. This one is called the interactive zero knowledge proof. This kind of zero knowledge proof, they're not the best for blockchain, where we have a lot of interactions. They are not the best for blockchain because of that. So the best zero knowledge proofs for blockchain are what we call the non-interactive zero knowledge proofs. And these ones require one round of communication. So the prover sends a single message to the verifier, and they do not need to be online at the same time for this to happen. So that is the advantage. The advantage is that you don't need to be online at the same time for this kind of proving to happen. But now look at this. The proof only sends a single message to the verifier, and the verifier is convinced. The verifier is convinced by that response. But for this other one, the verifier is trying as many questions as possible for this interactive. These non-interactive are the best zero knowledge proofs for blockchain. Now, of course, I've defined something here before I go to the details of these non-interactive zero knowledge proofs, because those are the ones we'll be looking at. Since we are interested with the blockchain, we'll be looking at the non-interactive zero knowledge proofs in a short while. But before that, before I just introduce them, I want to define what we mean by a proof system being sanctity. And so we say it's sanctity if the size of the proof, and you note the word, the size of the proof. If the size of the proof is less than the witness required. If the size of the proof is less than the witness required. What is a witness? I defined a witness yesterday, but let me repeat. A witness is a secret information that needs to be proven and authenticated. This is what that secret information is what we're calling a witness. So if the size of the proof is less than the witness, then we say that the proof is sanctity. Okay, so I now can look what the non-interactive knowledge proofs, zero knowledge proofs. Just before that, I've said here that interactive proofs are uncommon. In fact, I've already said this. They are uncommon in blockchain systems. And the reason is they're wasteful and need two parties to be online at the same time. So they need two parties to be online at the same time for verification, because what will be happening is Alex has to ask, then Wanjiru responds. And then as Alex again asks, then again Wanjiru responds. So you see, that asking and responding should be happening at that time. Well, of course, Alex cannot ask and then Wanjiru responds later. So that again, you come later and feel that you're not convinced and pose another question. And then Wanjiru will respond next week. And then again, you see that kind of need will not be making sense. So that conversation is supposed to be happening at the same time, so that once Alex asks a question, Wanjiru responds, then Alex feels that, I'm not convinced. I don't think you have this ability. Let him again do this. Then Wanjiru again does it. Then Alex thinks, no, I have to ask another question. And then Wanjiru responds. So that means they must be online at the same time. If it was on blockchain, which is done online, then it means they must be online at the same time. And so that is a disadvantage. So the non-interactive ones requires only one response. The proof only does one message communication. That means I can ask a question and then leave online. And then I'll come later to see if the response is there. And the response is only one, and I'll be convinced. So that is an advantage for the non-interactive ones. And so the non-interactive ones that we'll be looking at are two. The ZK, where ZK is just zero knowledge. And of course, I'll tell you what this is an abbreviation. So the whole of it is an abbreviation, and this another abbreviation. Now, this is the most recent. This is the most recent, and this has always been there. This one has always been there. This ZK stack is the most recent, and it came up because of some disadvantages of the ZK snack. So ZK snack has some disadvantages. And then this one comes now because of those disadvantages. So it's a better form. It's a better form. Although the two are still used online. In fact, this one is used by Zcash. This one is used by Zcash. But now this one is better compared to the ZK snack. Now, so what, okay, just before that, before the definition, I've said that most of the mathematics that are involved in ZK snacks and ZK stack will be polynomial equations and elliptic curves, and also the bilinear pairings and cryptographic protocols. So, but the mathematics that maybe when we reach at elliptic curve again, we shall see how the mathematics that are involved in this ZK snack and ZK stack. There's a lot of mathematics there on the elliptic curves. Now, so what is ZK snack, therefore? And I say it is an abbreviation. What does it stand for? So we need to know what it stands for. And of course, I had already defined something. I had already defined this term. I had already said that if a proof is sanctity, then it means that this proof is less than the witness. So that is what it means. But we shall see what it means again. Again, we shall look at that. So the ZK-SNAC is an abbreviation that stands for Zero Knowledge, Xantit, Non-Interactive, non-interactive, and then the R, the A is the argument, this AR stands for argument of knowledge. It's zero knowledge, Xantit, non-interactive argument of knowledge. So those words, I'll break them down so that we know what it means. Therefore, I'll break them down later, just before I'm done with the CK. But again, just to recall, this is a type of zero knowledge proof. So it's a zero knowledge proof where the prover is proving to the verifier, but does not want the verifier to know some particular information without revealing. So he doesn't reveal some information. There's some information that he should not reveal. Now, again, the other thing about this is that they don't need to meet. The prover and the verifier don't need to meet. They could be doing this online. But at every time as they do that, the prover must know what kind of information it does not require the verifier to know. Like the example we looked at when we began today's lesson, we saw where person A does not want person B to know the amount he has in his wallet. So that let them do the transaction, yes. Let him pay person B if he has to pay person B. But at the end of that, person B should not get to know even his address. There's no reason for knowing his. If you want to pay me money, you want me to pay you some money, why do you want to know my address? There's no need also. So there's that kind of information that you would want to that it remains yours. Now, so this point I've said, the ZK-SNACs serve as proof that one user possesses knowledge without disclosing that knowledge. So you don't need to disclose what you have, but prove that you have it. Just prove that you have the knowledge without disclosing what it is. I've already said this. I've already said that it has these mathematical procedures that are employed in blockchain. And part of that mathematics is from elliptic curves, polynomials, and so on. So it's not one type of mathematics. It's a combination of several mathematics put together. Now, so this proof, the ZK-SNAC, is made possible by a secret key, which is generated prior to the transaction taking place. So there'll be some secret key. Of course, the example we looked at earlier on, we talked of somebody encrypting message and so on. Then when you encrypt, you put that on the blockchain and so on. So the process of encrypting requires that there is some key. So there is the key, there'll be a secret key, and this secret key will be generated before the transaction takes place. In this one, I had already mentioned that the cryptocurrency Zcash uses this ZK-SNAC proof as part of their protocol. Now, so what are the features? The features is what I talked of, that I'll come and break down the name. The name begins with the zero knowledge. So let me admit this one first. Okay, so it's ZK, zero knowledge. So what does that mean? And again, we had already talked about that. Zero knowledge here means that as the prover does this transaction and so on, the verifier should learn nothing new, should learn nothing new about, apart from the fact that the prover has that information. So the verifier at the end of it should just know that the prover understands that information, but should not know what that information is. The verifier should not know what it is. So that's what I've said. The verifier learns nothing about the underlying data or information other than the fact that the prover is aware of that information. So that is the only thing. That as Alex does the transaction and so on, whatever the other person should know is just that the transaction. Let me talk about if it was a password, of course, or a PIN. Somebody should know that I know my PIN, for instance, without knowing what my PIN is. Somebody should know that I know it, and I can prove that person I know my PIN without necessarily telling him what my PIN is. I don't need to tell you what my PIN is for you to know that I know it, but I can prove that I know. So that is what we are saying, zero knowledge. It means that this verifier, therefore, the person who wants to verify that you know the information, the only thing he should know at the end of the verification process, the only thing that he should know is the fact that you know it, but you should not know what you know. Now, what is this sanctitness? And that is coming from the S. From the S, and we are saying that the proof size should be small than the witness. So I'm saying the proof size is quite small, usually a few hundred bytes, and it does not depend on the size of the statement being proved. So the statement being proved could be longer, but the proof is supposed to be short. The proof is supposed to be short. So that is what I mean by sanctitness. The proof size is smaller than the witness. The witness in this case is the statement being proven. The statement being proven is the witness. So the statement being proven should be longer than the proof. That is what it means by sanctitness. And then there's non-interactive, the N, non-interactive. Non-interactive, as we began, I said that the prover is supposed to send only one communication. So that's what it means. The proof is comprised of a single message from the prover to the verifier. So this eliminates the need for back and forth communication, where the verifier asks this question, the prover responds, the verifier is not convinced, asks another question. So that one is removed. That one is removed. So that is what non-interactive means. Then argument of knowledge. From here is argument of knowledge. So the proof guarantees that the prover understands the information at hand and is not simply producing proofs by chance. So you can prove by chance. And yesterday we looked at an example, and we say that if you are somebody who does not have that information, and you just overheard of it, and somebody tries to question you to prove, you can by chance get 50% right. But then the other 50% will be false. You will not get it right. And so the verifier is able to tell that you are an impersonator. You're not the real person that has that information. So arguments of knowledge it means that this proof that the prover is trying to produce should guarantee that this prover understands the information that he's talking about and is not just producing some good proofs by accident or by chance. So that is what argument of knowledge means. And therefore the word ZK snacks. That's what that word means, ZK snacks. Now, so how does it work? How does the ZK snacks work? Of course, I already said there's a lot of mathematics behind it. There's a lot of mathematics behind it, from polynomials to elliptic curves, cryptography, and so on, all those combined together. But how does it work? And the first step is the disadvantage I talked about. Remember, I said that it has a disadvantage that made the blockchain they need to come up with another zero knowledge proof other than this one. So the first one is the disadvantage I was talking about. And we shall see how it's a disadvantage. The first step, how it works, is the setup phase. And the setup phase is a trustworthy step, a trustworthy setup phase which generates public parameters such as a proving key and a verification key. Remember that we say that these keys are first of all generated before the transaction. They're generated before transaction. So there is this phase. This first phase is where first of all they generate these keys. So I've said is a trustworthy. Trustworthy here means that the prover and the verifier have to have trust in each other, that the keys that they have, nobody else has those keys. So that the verifier knows that this key actually is from the other person, and the other person also knows that, so that those keys are ones you can trust, so that you're not doing business with other people that may con you. Now, so this setup, the setup phase I've said is a trustworthy setup phase, which generates public parameters, and the word is public, not private. Public parameters such as proving key and verification key. This phase entails producing structured reference streams, which are used to generate and verify proofs. And remember, I've said that this setup here will form a disadvantage for these ZK snacks. It will form a disadvantage. And we shall see how it becomes a disadvantage. Then after the setup phase, we have the proving phase. The proving phase, now the prover generates a proof using the proving key that was generated here. The prover generates a proof using the proving key. And the witness, we've said this is the hidden information. This proof is supposed to persuade the verifier that the prover knows the witness without disclosing it. That the prover knows the hidden information without disclosing it. So the proof is supposed to actually persuade or convince the verifier. And remember, it's just one proof. For this type, we said this is non-interactive zero knowledge proof, and therefore communication is just supposed to be once. So as you do it, That once, let it convince the verifier that you have the knowledge, that you know the knowledge you're talking about, you know the information you're talking about, and you're not just doing it by chance. And then there's this verification phase, therefore. The verifier comes in and then checks the proof's validity using the verification key, which was generated in this setup phase. So the verification procedure should be efficient, generally taking the same amount of time regardless of the magnitude of underlying computation. So that means even if the computation is huge or small, then the amount of time should just be the same. And remember the disadvantage I talked about. Now, this is a repetition. I said ZK snarks are based on polynomial equations and elliptic curves. The other point is that ZK snarks are used in cryptocurrencies such as Zcash, which I also talked about, to produce private transactions in which the transaction data, such as the sender, the receiver, and the amount, are hidden from the public. We said we have people on the blockchain, viewers. We have viewers on the blockchain. So those viewers, they're not supposed to know Alex has sent me some amount, or it's me who has received the amount, or how much I have received. I'm not supposed to get that information. So the fact the person is encrypting, you encrypt, that information will be there. Of course, people will be seeing it. It should be encrypted so that whoever is seeing it cannot understand what it is. And of course, they don't have the keys. They don't have the keys. It's only the two of you that have the keys. Now, the disadvantage I talked about, the major drawback of the ZK snark in the implementation is the requirement for a trustworthy setup phase. Why is it a disadvantage? Why is this a requirement? And of course, we've already seen that this is a point where we have things like the keys, the proving key and the verification key being generated. But we're saying that this phase has a disadvantage. And the reason is that during this phase, and of course you saw there was a common reference string being generated, and this may jeopardize the system's security if not executed correctly. What was it for? Just go back there. Is it here? This phase entails producing structured reference strings which are used to generate and verify proofs. And they are saying that if during this process, as they produce these structured reference strings that are used for generating and generating these verifying proofs, if this process is not done correctly, then the attackers or the people on the blockchain may be able to capitalize on it and jeopardize the whole process. They may capitalize on that if that process is not done correctly. But if it's done correctly, then it does not become a disadvantage if it's done correctly. So in fact, I've put it here, and I've said, however, the efforts to address this issue, such as using multi-party computation to divide confidence across different parties. So there's that the modern cryptography, of course, and the use of blockchain, there are efforts to reduce on the impact of that disadvantage. Now, so I said because of that disadvantage, there came up the ZK stacks. There came up the ZK stacks. So ZK stacks just comes in because of that one disadvantage, of course, which is being addressed. But of course, we have the ZK stacks because of it. What does it mean? Again, it is an abbreviation. It's an abbreviation. The first two letters, zero knowledge. The verifier learns nothing about the underlying data other than the fact that the prover is aware of it. Now, there's a slight difference from this and the other one. Of course, we have the S, it was not there. And this one means scalability. Scalability. So ZK stacks are intended to handle massive computations efficiently, producing proofs that stay manageable and that stay manageable as the size of the data or calculation increases. So these ones, they are used to, if you have data, huge data, or you have several computations or several proofs, and then this one will work. This one will work because of the scalability. So the scalability, again, is another disadvantage that is not with the ZK snacks. And this one comes with this. So it can handle massive computations. And it can produce proofs of manageable size. And even if there are very many calculations, again, this one will still handle that. Then there is this T that stands for transparency. I think I skipped somewhere. Did I skip something? It's okay. So I think the only thing I needed to say was just that this is an abbreviation that stands for zero knowledge, scalability, transparency, and argument of knowledge. That is the only thing that is missing here. That is ZK stacks is an abbreviation. And this abbreviation stands for zero knowledge, scalability, transparency, and argument of knowledge. So then I went to what the abbreviation stands for, what each of those letters stand for. Now, transparency here, it means that the ZK stacks eliminate the requirement of trustworthy setup. So there's trustworthy setup first, which was first number one in the ZK snacks. So the transparency, this T comes now to replace that, so that we do not need this trustworthy setup phase here. This one does not have that phase. So how do they do it? They rely on publicly verifiable randomness, which increases trust and decreases the risk associated with the setup phase, this trustworthy setup phase in the ZK snacks. So they rely on publicly verifiable randomness, and which increases and trust, and then it decreases the risk of that first phase in the ZK snacks. Of course, we have the argument of knowledge it will be the same as it was in the ZK snacks, that it's to ensure that the prover understands the information rather than simply producing valid proofs by accident. So we want to be sure that this prover is not just giving us proofs which are valid, of course, and by accident. So it's just stumbling on the proofs and then giving us. We want to be sure that that is not the case. So today I said I will just begin with this theory, and then we finish with the mathematics, which is an example 4 above. Now, how does ZK stacks work? Now, we have this setup first, but it's not the same as the one in the ZK snacks. And I began by saying that unlike the ZK snacks, the ZK stacks don't need the trusted setup. Instead, they use publicly verifiable randomness to generate parameters required for the proof. So the removal of this trusted setup first reduces the risk and therefore makes the ZK stacks to be more safe and easier to deploy. Then from there, we have the proving phase, where the prover encodes the computation as a polynomial and then employs interactive oracle proofs. And of course, I said we have a lot of mathematics here to demonstrate that the polynomial fulfills the required properties. Now, this will then entail things like breaking down the computation into a series of steps that can be checked efficiently by the verifier. The verifier comes in at the verification stage or phase. So the verifier will check the proof by sampling a few points of the polynomial and then confirming that the sampled values meet the requirement. So this will then assist the verifier to confirm that the proof is valid and therefore the computation is complete and so the transaction can proceed. So that is how the ZK stacks work. So we've seen the ZK stack, so we know what it means and we know how it works. We've also seen the ZK snacks. Both of them are used currently, but I've said that the ZK stacks came up later after there was discovered that the first phase in the ZK snacks had some loopholes which could be capitalized by the viewers on the blockchain, which could be capitalized. So and then it comes in to seal that loophole. Now, so I want us to go to some example here. Of course, yesterday we entered, or this is where we ended, where we had done an example. And in that example, we then thought of what if somebody was listening to communication and this person tries to impersonate the prover. And we did an example where this impersonator scores 50% correct, and then the rest, the other 50% is wrong. The example was here. This was the example. So let me just again look at this example. It began with example 2. Example 2, we had it was a conversation between Alex and Cyprian, and they had selected the prime numbers and then gotten the product of those two prime numbers, n, and n was 7081. So this 7081 was made public. And since it was made public, the impersonator was in possession of it, so got to know what it was. Then the other information that was public was 5629, which was x square. So this again was public. So since it was public, and of course, in that example too, Cyprian knew what x was. So he used that x and to get it square. Use the x to get it square, but the x was that secret information, which we are calling the witness. It was the witness. So he did not want it to be known by anybody. Now, there's this Eve who was following, and Eve saw this n and then saw the x square. And he wants to pretend to be now the Cyprian and proceed with the transaction. Wants to proceed with the transaction. So then he has to prove that he is the Cyprian, because we don't know anything about Cyprian apart from the fact that he has some knowledge which he has proved to have. He has proved to have it. So if anybody else is pretending to be the one, then that person is also supposed to prove. So this guy was smart. This Eve was smart to prove. The Eve knows that since there's an x square and there's this 7081, most likely I'll be asked about the square root of x, the x square, the square root of x square. That's what I'll be asked. That is what this smart guy thought. And the smart guy then thinks, I need to send to Alex 2 numbers. And when Alex gets those 2 numbers and gets their product should give him x square. And of course, that is the same thing that Cyprian did. Chose randomly 2 numbers. And then those 2 numbers, which were selected randomly, when Alex tried to multiply them, they gave him x square. So that is what Eve knows is supposed to happen. So Eve chooses a random number, and he chooses 170. When he chooses 170, this is U1. He squares it. She squares this 170 and gets this 576. Of course, after reducing it to mod 7081. And then after that, she multiplies this square. She multiplies, before multiplying this square, she gets its inverse. She gets the inverse of this square, mod 7081. And that inverse is 2053 when you do it. Now, since she has this inverse, she calls this inverse x2. She calls it x2. And calls this square, which is 576, she calls it x1. No, this inverse, after getting this inverse, just a minute, this inverse, after getting this inverse, you must get U2, the square of U2, by multiplying this inverse by x square. By multiplying by x square, that is the first thing. So this inverse multiplied by x square, you get the square of U2, which is 145. This is what she calls x2. And then this one calls it x1. She sends x2 and x1 to Alex. Alex confirms whether that their product is x square. So multiplies these two. And to his surprise, he finds that they're equal to x2. So he's beginning to feel that this guy is proceeding in the right way in terms of the proof. But then he has to verify. He has to verify now, since you see, he has just sent the two numbers. Now, Alex is supposed to ask him to get the square root of each of them. Alex asks, find the square root of, give me the square root of 576. She goes back to her computation, and you see 576 was a square of 170. Was a square of 170. So she sends to Alex 170 as the square root of 576. She's right, because Alex will just, to confirm, Alex will just take 170 and square it, mod 7081. And when he does that, he'll find that the answer is 576. So she's right. She has scored the first question. She has scored the first question. So the second question, Alex will ask her, find the square root of 145. Give me the square root of 145. And you remember, this is the interactive zero knowledge, where you ask this question, you ask the other question, you ask the other question, so that you are convinced. She is not able to get the square root of 145 because 145 was just a square. She just found a square by multiplying the inverse by the square of x2. When she multiplied these two, the product was a square. So she cannot get the square root. She just got a square. She doesn't have the square root. You see, for the other one, she was able to get the square root because she had squared a number. She had squared a number to get that is square. She had squared a number to get, so she knows the square root of 576 is 170. She knows that. She had this 170 from the start. She's the one who chose it. She chose it. But she did not choose the square root of 145. So she doesn't know it. She cannot get it. She cannot get the square root of that mod 7081. These are very difficult arithmetic. So she fails on that level. She fails that. So she has scored only 50% and failed the challenge. You're able to tell that she is an impersonator, because if she will not be an impersonator, she'll be having the square root of those two numbers. So that means she cannot, she doesn't know what x is, because she cannot get the square root of x squared. Because for you to get the x, you must know the square root of x squared. And what is x squared? X squared was a product of two numbers. Was a product of two numbers. So for you to know x, you must know the square root of this and the square root of this. So if you know the square root of these two, it means you know the square root of x squared. Because these two give you, their product gives you x squared. But you only know the square root of 556, and you don't know the square root of 145. That means you don't know the square root of, so you don't know x. You don't know x. That's what it means. So you don't have that information. And so when we left yesterday, we said that that is soundedness. We said the soundedness, when we're looking at some of things we look at to confirm that the protocol is zero knowledge. Then we say that the test should be sound. The test should be sound. And I explained what sound means. When you say that a test is sound, it means that if there's an intruder, coming in to pretend to possess the same knowledge, the same information, and is an intruder. This intruder should not be able to completely convince the verifier that though the prover, this intruder may get correct some questions, there are other questions the intruder will fail. And of course, the intruder will only get 50% correct and then fail 50%. So that's what we mean by the test being sound. That the intruder, Eve, must know the value. No. The intruder, okay. For Eve to know let me just read what I wrote. That is, to pass the test, okay, it's the same thing. So it means Eve cannot pass the test if she doesn't know what X is. So if she cannot pass the test if she doesn't know what X is. If she knows what X is, then she'll pass the test. But since she doesn't know X, she will get half of the questions correct and then fail half of the questions. So she will not pass the test. In other words, for you to pass the test, you must prove by getting all questions correct, just the same way here. So the test must be complete. So for the test to be complete, it means the person who claims to have the information must pass all the questions, must always pass. So if he always passes, then we say that that test is complete. And the other thing we say that the test should be zero knowledge. And what that means is that the verifier, at the end of it, at the end of the process, the only thing the verifier will get to know from that proving and verification is that the person who claims to have the knowledge has it. That is the only thing the verifier will know. The verifier will go home convinced that the prover has that knowledge, has that information. But the verifier will not get to know any other information other than that. Will not get anything new other than the fact that the prover has that information. Now, so the example I wanted to look is this algorithm 2 that looks at the identification scheme, zero knowledge identification scheme, zero knowledge identification scheme. This is an algorithm, and it is using two large prime numbers and then gets the product of those two prime numbers. So let's say that the recipient has the secret numbers, this, which he doesn't want anybody to know. And that he also has this. And he doesn't want anybody to know. And of course, he's supposed to be asked to prove that he has this kind of information. Let me just explain what this means. What is this? This is just the same as 1 out of SI square. Same as 1 out of SI square. That's what it means. In fact, what it means is the same as the inverse of SI. SI inverse, then you square that inverse. When you square that inverse, what you get is SI raised to -2. So it was just inverse, and then you squared. And you know what an inverse is? The inverse of 2, for instance, is 1 out of 2. That's why I said this is just the same as this. So that if it's this inverse and you're raising it to 2, it's the same as 1 out of 2 out of 2. 1 out of 2 raised to 2. The same as that. I just want us to get to know what this means before we proceed with the algorithm. Yes, so this algorithm, we've said that we have two prime numbers, large prime numbers, and then the witness is S1, S2, S3, all the way up to SK. And the other witness is this, mod N. And how was SI chosen? SI was chosen just like in the previous examples, was chosen so that it's relatively prime to N. It's relatively prime to N. So, okay, this is the witness. This is the witness. This is the only witness. Then you get the square. One out of this, then is square. One out of this, then is square. Then when you square, just as we are doing in the previous example, you send Alex the square. One out of S, one out of S, one out of S, then is square. When you square one out of S, what you get is 1 out of S square. The only thing is that we have SI. I means 1, 2, 3, 4. I is 1, 2, 3. That's why you see I have 1, 2, 3 up to K. That is what I means. I are just the integers. Good. So the witness is S1, S2, S3 up to SK. Take this S1, S2, S3 up to SK, I divide 1 by this, then you square the result. When you square the result, send it to Alex and claim that you know S1, S2, S3 up to SK. Claim to Alex that you know what S1 is, what S2 is, and so on. So Alex wants you to prove. So Alex receives, on receiving this, wants to check whether you know what indeed S1, S2, and so on is. So it's now your time to prove. And for you to prove, the first thing you do, you choose a random number. And this random number from yesterday, we said is better when you choose it and if it's relatively prime to N. You choose this random number that is relatively prime to N. And then after choosing this random number, just as we did, but slightly different, in this case, slightly different, compute the square of this random number. Call it X. Compute the square of this random number. Call it X. Send it to Alex. Now, so when Alex gets this, he selects numbers B1, B2 up to BK. Because we had sent him this, we had sent him V1, which has S1, S2, S3 up to SK. So he also sends you these numbers. And look at these numbers. He's choosing them between 0 and 1. So these numbers are chosen between 0 and 1. So it means they are fractions. They're fractions. For instance, it could be a half there, could be a third, could be a fourth, and so on. Numbers between 0 and 1. He sends you those numbers from 1 up to K. Sends you those numbers. So when you receive these two numbers, you're supposed to convince him that you know what S is. What you do, the first thing you do on receiving these two numbers, first of all, take your the R that you have the R. It's you as the R. Then you know your S1. Take your S1 and raise it to B1. Take your S2 and raise it to B2. S3 and raise it to B3. And then multiply all this. Remember, these powers are fractions. These powers are fractions. So raise to S1, S2, and then multiply by R. You know it's you who chose the R. And when you chose R, you did not send R to Alex, you send him R square. And now since you have the R, multiply by R. And then send Alex the product. Send him this product, call it Y. Send him that product, call it Y. Just call it Y and send him. When he receives the Y, he wants to verify whether the square of Y is the same as X. He wants to verify whether it's same as X. So what does it do? It takes the Y that you send him, because X is this. X is the one you had sent Alex here. It was the square of R. It was the square of R. So Alex now gets this Y, wants to confirm whether taking Y, squaring Y, and multiplying by the V's, you had sent him V. You had sent him V, VI. Now he wants to confirm whether if he takes Y squared and multiply by V raised to B1, V2 raised to B2, V3 raised, it will give him X. That's what he wants to confirm. But he will confirm. In fact, he will get that this is true. He will get that that is true. And then when he gets that is true, he chooses other B's, B1s, B2s, different ones, and again sends them to you. So that you do the same process, you repeat the same process from 1 to 4 until he's convinced. So after you send him another one, again, although he sees that Y square multiplied by that gives him X, he's still not convinced. He chooses another B1, B2, and so on, and sends them to you, and so on, so that that process continues. Now, that is the identification scheme. The identification scheme, I have noted something here. I've said it's worth noting that the robustness of this identification scheme is dependent upon the difficulty of computing the square root. I've said that computing the square root in modular arithmetic is not easy. So the difficulty, the robustness of this method, what makes it secure? What makes it secure is the fact that it's very hard to compute the square root modular in modular arithmetic. Now, so at your own time, again, look what this example 4. Example 4, I've come up with a way. I've looked at how now that if supposing you went to a bank and you wanted the ATM card, how the PIN will be produced up to the time that the card will then be printed for you. So these are the steps. So you just look at those steps, and then when we get time, we shall look at those steps again and explain. So it goes up to the time the card is printed for you. And the card is only printed for you at the stage when they know that now the PIN which you provide is, of course, it's you to provide the PIN. It's you to provide the PIN nowadays. It's not like long time ago where you go to a bank and then you will get a PIN in some envelope. There's a time you were to be given a PIN, some PIN in an envelope. Then you're asked, you go and input. Then you are given some step where you can now change. These days this PIN, it's just to put, and then it's printed. The card is printed with the PIN already. But of course, even the other one where you are to be given, at that point when you are going to input your own, when you change, that PIN is stored somewhere. So after it has been stored, it's now the card is okay. You can now use that card. But you look at these steps. You look at these steps later, and then when we get time, we can discuss. Thank you.